Hi there, this is Dr. Matthew J. Traum from Engineer Inc. The purpose of this video is to showcase our newest hands-on learning module. This is a take-home laboratory. This particular one demonstrates the Reynolds Transport Theorem and the conservation of momentum. That's the equation that states that if you have a fluid and you somehow change its direction or change its speed, well, that change in velocity imparts a force on the surrounding apparatus. And that's exactly what this experiment does. So just as a reminder, we are developing an online fluid mechanics class at the undergraduate level for engineering students. The course is offered completely online. There's online reading, online lectures, assessments are done online, but there's also a hands-on component. So we've miniaturized a number of pretty interesting laboratory experiments. We send those out to the remote learner. That student then assembles the labs, runs the laboratory experiments, does the data analysis, and so forth to get a hands-on experience that's complementary to the online course. So as I mentioned, this is a momentum conservation apparatus, and essentially the way that it works is there is a computer fan here. The computer fan has a little power cord which runs off the screen in that direction. I have a variable speed control that I can use to set the fan at pretty much any speed that I want. The fan takes fluid here underneath where there's this little opening, and then the fluid changes direction and is forced upwards through this nozzle, and it's that change in direction from radially inward to upward that induces the momentum change that imparts a force. Since the fluid is moving upwards, the induced force, of course, is downwards, and here is a scale, and so the scale is essentially measuring that force, and I can just read the force right off the scale, but to make it more clear for this video, I've got a computer set up here to show you guys the mass. I'm, of course, interested in force, and so we need to use the knowledge of gravitational acceleration to convert this mass into the equivalent force, and that's how I back out the force that's produced by the fluid, again, coming out of that nozzle. An additional component of Reynolds Transport Theorem is you have to know what the velocity change to the fluid was. So the fluid is sucked in from the ambient environment here. This fluid is the air. It's essentially not moving, so it has an initial velocity of 0. But as it comes out of this nozzle, I've got here a pitot-static probe, which has both a total pressure port and a static pressure port, and the combination of those two pressure signals, which come off here, are fed into my Dwyer manometer, Dwyer Mark II manometer, which is here. It's reading in pressure. This is inches of water. Here's the scale. But that pressure difference using a pitot-static probe equation can be converted into a velocity. So this probe is essentially telling me the velocity of the fluid coming out of this nozzle, and it's measured quantitatively here, and then I can compare that velocity to the force that is induced on the scale by the apparatus. So that's essentially how it works. I'm going to turn it on now, just give you a demonstration to show you that I do get actual numbers. So I'm just going to plug the fan in here, and here we go. So here's the fan turning on. You can hear it spin up, and of course as it does, the velocity measured by my Dwyer manometer increases, and the mass went from 0 to about 39 grams, which of course means that there's a force being produced on the scale that wasn't there before. Now, I do have the ability to change the speed of the fan, so I would record this as a data point, about 39 point... about 38.9 grams and about 0.225 or 0.25 inches of water. And now I can change the velocity of the fan, and we should see a change in the instrumentation to reflect a different velocity. Okay, so now I've dialed the velocity down, and we can see here on the manometer a reduction of velocity to, about 0.16 or 17 inches of water, and a corresponding reduction in the mass, which means that the force is reduced to about 30 grams, which is what we expect as the velocity goes down. Of course, the imposed momentum also goes down, so that's no surprise. Okay, let me unplug the fan so you can hear me again. All right, so I've got the fan shut off now. As we expect, the velocity goes back down to 0, and the mass should be restored also to 0. There's a little bit of offset there, but that's all right. That's just an artifact of the experiment. And that's it. That's the entire demonstration. So I'm going to be putting up more videos as I complete these prototypes and get them operating. So please check back again for more videos from Engineer Inc. showcasing our hands-on learning module take-home fluid mechanics experiments. Thanks for your attention. See you soon. Bye.